In this video, we're going to continue talking about buffer solutions. Remember, a buffer solution is a solution that contains a weak acid and its conjugate base, or a weak base and its conjugate acid. And it functions by allowing only small changes in pH when an acid or a base is added to it. So it's a solution that resists large pH changes. So if a small amount of acid is added to it, it's going to react with the base component of the buffer and be neutralized. If a small amount of base is added, it's reacted with the acid component of the buffer and neutralized. So in the last video, we looked at a buffer solution, we calculated its pH, and then what I want to do now is calculate the new pH, right? We didn't say the pH doesn't change at all, it just doesn't change a lot. So what is the new pH when an acid is added to it, and then what is the new pH when a base is added to it? So I'm going to start by just recopying down the last example that we did in the previous video. So we had a buffer solution, and I'm just going to write down part of it. It contained 0.45 molar formic acid and 0.55 molar sodium formate. Again, we didn't care about the sodium ions, so if it's easier, you can just kind of ignore that and think about formate ions. We said that the Ka of formic acid was equal to 1.8 times 10 to the negative fourth molar. And then we calculated the pH of that buffer solution, and we got a pH to be, which I just want to write down for reference here, of 3.82, right? So we made our little ice table. Our initial concentration of formic acid was this. Our initial concentration of formate ions was this. We did the plus X minus X stuff, solved for X, which was hydroxide ion concentration, took the negative log of it, and we got 3.82 for my pH. So what I want to do now is we're going to calculate the new pH after 0.10 molar hydrochloric acid is added. And let's actually make that an A because we're going to do two things. And then B, we're going to calculate the pH after 0.10 molar sodium hydroxide is added. And we're going to go back to the original buffer solution for that. So instead of adding acid to it and then adding base to the one that we added acid to it, we're just going to go back to the original. So basically, it's kind of two separate problems, really. We're going to have this buffer solution. We're going to add acid to it. We're going to calculate the new pH. Then I'm going to go back to this buffer solution. I'm going to add base to it instead and then calculate the new pH. Remember, buffers resist dramatic changes in pH, so my pH is going to be different than 3.82, but not dramatically. It's not going to like jump down to 1 or jump up to 8. It's going to kind of still be in that same ballpark. So the first thing we need to do is write our neutralization reaction when we do this. So remember, when I add an acid, which is what I'm doing in this first one, so we'll do part A here first, that acid reacts with the base component of the buffer. And in the previous video, I had us write those neutralization reactions. So that's the first thing we're going to do here. So part A, we're going to first write the neutralization reaction. Once we do that, we're going to make what's called our change table. So write or make, however you want to say it, the change table, which is going to be a new table different from our ice table. And then I write ice, write our change table. Sometimes I call it the neutralization table because that's what it is. So we're going to write our change table. We're going to use that the new concentrations of our acid. I'm just going to use HA. In this case, it would be formic acid, and its conjugate base. In this case, it would be formate, right? Because we're going to neutralize it. I'm not going to have as much base as I used to because the base component is neutralizing the acid. I'm actually going to form more of that acid. So we're going to have to write a neutralization table or change table. Let me put neutralization here also. Neutralization table is what I called it for 16 years when I taught in Michigan. Here they call it a change table. So I'm trying to adapt, but every once in a while say neutralization. So we're going to make that change table. We're going to calculate our new concentrations. And then once we do that, we need to plug the new concentrations into an ice table, which sounds like a lot of steps. I'll give you a shortcut in a little bit, but we're going to do kind of the full method first. So these are our steps. So neutralization table for part A. And actually these steps are going to be true. I'm going to get rid of A. That's going to be true for both of these, right? Anytime you're adding an acid or a base to your buffer, you're going to write your neutralization reaction. You're going to make a change table. Using that change table, you're going to get your new concentrations, and then you're going to take those values and plug them into an ice table. So let's do part A. So A, we're adding 0.10 molar HCl. And I did say I want us to just be able to go right to the net ionic equation. Anytime you're going to see a strong acid, we're going to think H3O+, right? It doesn't matter what that strong acid is. If it's HBr, I have H+ in water, which is hydronium ions, and Br-, which I don't care about. If I have nitric acid, I have H+ in water, which is hydronium ions, and nitrate ions, which I don't care about. So anytime we have a strong acid, the part that is going to be important for us is hydronium ions. So that's how I'm going to think of that. That's going to react with the base component of my buffer. So if we go back up to our original buffer solution, I have formic acid, and then I have 0.55 molar formate. That's my base component. So that's the one I'm going to use for my neutralization table. So I'm going to have hydronium ions plus the base component of that buffer. That's going to produce water, and in this case, formic acid. And then let me move this down actually. I just want to be able to write change table over it. So when you look back in your notes, you have it labeled. Or neutralization if I say it the old way. Table. So that's what we're writing here. So what I'm going to have, and different instructors kind of write this differently, but I'm going to basically have my old concentrations. And it's not really that they're old, it's just the ones that were given in the problem. So you could say original concentrations, initial concentrations, however you want to do it. Old works for me. Initial is probably better, but it's going to be these values that were given in the problem. So old, initial, original, however you want to think about it, but the ones that you were given, right? When we make the buffer, what were their concentrations? I'm going to have a change, and then I'm going to have my new concentrations. Those new concentrations then are the ones that I'm going to then plug into an ice table, right? We're going to put our new concentrations into our ice table. So my original concentrations, my initial ones, my old ones, those are just coming from the problem itself. So scrolling back up just so we can get them, I have 0.45 molar for my formic acid. I have 0.55 molar for my formate ions. So this was 0.55 molar. This was 0.45 molar. Be really careful that you put the right ones in the right spot. That's a liquid. The others are aqueous. And then my initial or original or old, whatever you want to call it, concentration of acid, right, is coming from right here, right? Every little bit of hydrochloric acid is H3O plus and Cl minus. So if I have 0.1 molar HCl, I have 0.1 molar acid. And then what I'm going to do is it's just a limiting reactant problem at this point, right? I'm going to take the smaller of the two reactants, right? If you remember limiting and excess reactants from 151, right? A reaction can never proceed further than your limiting reactant, right? So I'm going to take the one that's smaller. In this case, because it's just a 1-to-1 ratio, I can literally look at these two numbers. I can see which one's smaller, and I'm going to subtract that from both of them, right? Remember, you can never lose more than you have. If I only start out with 0.1 molar, I can't lose 0.55. But if I start out with 0.55, I can lose 0.1, right? You can never lose more than you have. So I'm going to take the one that I have less of. I'm going to subtract that from both reactants, because we always lose from the reactant side, and then I'm going to add that to the product side. So essentially what's happening is 0.1 molar of my acid is reacting with 0.1 molar of my base, and then we always add to the product side, producing 0.1 molar here. And I am ignoring volume changes right now, right? Molar is moles per liter. It's technically a 1-to-1 mole ratio, right? 1 mole, not necessarily 1 molar. I am ignoring volume changes. When we do this in our titration problems in a future video, we're not going to ignore volume changes. So if you're like, well, my concentration isn't really that anymore because of the additional liquid, I get it. We're just ignoring that for now. So maybe we should make a note. Ignore volume changes. And when we do titrations, we're not going to do that anymore, but for our buffer problems, we will. So just ignore volume changes for now. So kind of back to this again. I'm going to look at my two reactant concentrations. I'm going to take the one that's smaller. I'm going to subtract it from both reactants. I'm going to add it to the product side. And then to get those new concentrations, we're literally just going to do that math. This is going to 0, right? We've neutralized all of it, so 0. This is now 0.45 molar, and this is now 0.55 molar. So those are my new concentrations. We're now going to make an ice table, just like we did in the previous video when we were calculating the pH of our solution, but we're going to use these values to plug into that ice table. Now make an ice table. And again, if you can do this by just setting it equal to Ka, by all means, you can kind of skip the ice table. I'm going to write down all the steps for now, though. So our ice table is going to be our acid, right? We're going to write our acid dissociation equilibrium equation. So formic acid reacting with water, forming hydronium ions, plus my conjugate base. And then the initial concentrations that I'm going to use are going to be those new concentrations, right? If we go back to our steps, we're going to use those new concentrations. So I'm still going to write initial, but it's my new ones. And for the ice table, it is my initial because it's not equilibrium. So for formic acid, I'm going to have 0.55 molar. Don't don't care about water, 0. And then for formate ions, 0.45 molar. Oops. Writing with my highlighter never looks good. And then just the normal, we lose some unknown amount called x, add x, 0.55 minus x, 0.45 plus x. And then we're going to plug that into our equilibrium constant expression. So we're setting it equal to Ka, which was 1.8 times 10 to the negative 4th. You can scroll back up to confirm that right here. And then because that's less than 10 to the negative 3rd, we are going to do that assumption again where we assume the minus x and plus x are negligible compared to those new initial concentrations. So I'm going to have the concentration of hydronium ions multiplied by the concentration of my formate ions over the concentration of my formic acid. I'm going to solve for x, which is going to be my hydronium ion concentration. So I'm grabbing my calculator. And I'm going to double check that. And I got 2.2 times 10 to the negative 4th molar. And then my pH is the negative log of that, which comes out to be 3.66. So if I take that number, and then I'm just going to scroll up here real quick to compare it, right? This was the pH of my buffer solution before we added base or acid to it. And then after I added acid, right, I got, what did I just say, 3.66? Sorry guys, 3.66. So again, my pH did change. I went from 3.82 to 3.66, but it's just a small change, right? It wasn't a huge change. If I would have added this to water, I would have started out with a pH of 7 because that would have been the pH of water, and it would have jumped down to a pH of 1, right? The negative log of 0.1 is going to be 1. So I would have gone from 7 all the way down to 1, right? It would have been a big jump. Adding this amount of acid to a buffer instead of water, I just went from 3.82 to 3.66. And then again, just make sure you think about it, right? If you goofed up somewhere in the math, you can catch some of those mistakes. It should be a small change. If you got a big change, something went astray. And then also I am adding acid, so I expect my pH to be smaller than the original. If this number would have come out bigger, right? If I would have got like 3.9 or something, I know I goofed up somewhere because we're adding acid to it, not base to it. So my pH should be more acidic. So you do want to kind of think about that as you go through these problems. So we're going to do part B, and it's going to be the same process. I'm going to write my neutralization reaction. I'm going to make my change table. I'm going to calculate my new concentrations after that base has been neutralized by the acid component of my buffer. We'll take those new concentrations, plug them into an ice table, calculate my pH. So I have a 0.1 molar sodium hydroxide solution. Again, sodium we're going to ignore, so I'm going to write my net equation when I write my neutralization reaction. And it's going to be between hydroxide ions and then the acid component of my buffer, which is my formic acid. Oh, I wrote that wrong. Sorry, guys. If that's confused you for some time now, I'm sorry. CH2OH. I didn't all of a sudden add an oxygen, right? Those wouldn't be conjugate acid-base pairs if I had that 2 there. So let's write that reaction. Sorry, I'm distracted now. Hydroxide ions plus the acid component. That's going to be my neutralization reaction. So going back down, right, part B, I am going to have my hydroxide ions. I am going to react that with the acid component of my buffer. I'm just scrolling up to see if I wrote formic acid incorrectly anyplace else. That's going to produce water plus formate ions. So what I'm making right now is my change table. So my original concentrations, maybe we'll use that instead of old. Original, my change, and my new. So again, those original concentrations are coming from the problem itself. So we have to scroll back up again here. The concentration of base that I'm adding is going to be 0.1 molar. So let's go back down and stick that in there. The concentration of formic acid is coming from up here, so 0.45 molar, and then 0.55 molar for formate ions. Right, pure liquid, and then 0.55 molar. And then again, the change, this is a limiting reactant deal. I'm going to look at both of my reactants. I'm going to take the number that's smaller. I'm going to subtract it from both of them. I'm going to add it to the product side. So 0.10 is smaller than 0.45. So that's the one I'm going to subtract from both sides. And then I'm going to add it to the other side. And then we're going to do that math. So all of my base has been neutralized, right? I don't have any of it left. I have 0.35 molar formic acid, and I have 0.65 molar formate ions. So now I'm going to make my ice table. And we're going to plug those numbers into my ice table. So my acid plus water going to hydronium ions plus my conjugate base. And then again, we're using those new concentrations. So this is the number that's going to go here. This is the number that's going to go here. So 0.35 molar, 0.65 molar. And then it reacts. We don't know how much it's going to lose, so we're going to call it X. I'm going to write minus X, but again, I'm just going to ignore it because Ka is small. The reason we would want to write it, I know it might seem silly to like write it and then get rid of it, is that if I was asked to solve for the concentration of any of these other species, right? If I wanted to know what the concentration, and I could certainly ask for this, I often and usually do. If I wanted the concentration of this, we would have to, after we solve for X, go plug it back in. In this question, I'm just asking for the pH, so really this is the only part we're concerned with. But again, we don't want to forget that we are subtracting and adding, even though when I solve for X, I'm going to ignore it. So solving for X, 1.8 times 10 to the negative fourth, my Ka, multiplied by the concentration of hydronium ions, multiplied by the concentration of formate ions, divided by the concentration of formic acid, right? Again, we're ignoring these because Ka is small. And then solving for X. And I got 9.7 times 10 to the negative 5th molar. I am going to double check that real quick. And I got the same thing. That is hydronium ion concentration, so pH is going to be the negative log of that number. And I got 4.01. And then again, we really just want to think about, does this make sense? I added base to it, so my pH is more basic, right? It went up from where it was originally, so that makes sense to me. So I'm just going to bring that number up here so we can compare again. Kind of running out of, didn't leave myself a good spot, but again, this is what we were starting out with. This time I added base to it, I got a pH of 4.02. So it did go up a little bit, right? It doesn't, buffers resist big changes. It's not that they resist all changes. It went up because we added base, right? So my pH is more basic than what I started out with. Still acidic, but more basic. And then the change is pretty little. If I would have added this to water, my pH would have gone from 7, right, which is what the pH of a pure water solution is, and it would have gone down to 13. If you were to figure out the pH of just a negative of a 0.1 molar sodium hydroxide solution, you would get 13 as your answer. So again, a big change if you added it to water. If you add it to the buffer solution, only a small change because of this neutralization, right, that's occurring. Right, that base that I'm adding is being neutralized by this. I end up with 0 there. It still have these contributing to the pH, but this base that I added is neutralized. I do want to consider a couple more things with this problem before we move on to another one. So I'm going to just rewrite our reaction here. So my formic acid plus water going to hydronium ions plus my conjugate base. So just my original acid dissociation equilibrium equation. These, of course, are aqueous. And then adding an acid or a base to this reaction, right, this buffer solution, but this reaction that's at equilibrium is also an application of Le Chatelier's principle. Right? We're taking a reaction that's at equilibrium and we're applying a stress to it, right? We're adding acid or we're adding base. So we're knocking it kind of out of equilibrium and then it needs to reestablish equilibrium. So looking at this, right? Our first one where we added acid. If you would have gotten this question on chapter 13, right? If I said, which way does this reaction shift if hydronium ions are added, you would tell me it's going to shift towards reactants, right? This side, I have too much of it, so I need to decrease it, and I'm going to shift in that direction. So this shifts towards reactants. So if I was to look at my concentrations of this number and this number, when I add that acid to it, because it's shifting towards reactants, I'm going to expect this to be smaller than before the shift, right? Because it's shifting away from it. And I'm going to expect this to be bigger because I'm shifting towards it. And if we go back up to the work that we did, I'm looking at part A here, right? So I started out with 0.45 molar formic acid, and I'm going to do some scrolling here. We said that this is the one that should get bigger, right? Because we're going towards it. And if I look at my new concentration, it's bigger than what we started out with. We said this should get smaller, and if I look at my new concentration, it's smaller than what we started out with, right? We are shifting in that direction. Sorry, am I going too fast here? And then going back down, part B, we added hydroxide ions. And this one might not be super obvious at first. Let me get rid of some of this stuff. What we're doing when we're adding hydroxide ions is we're removing acid, right? What those hydroxide ions are going to do is they are going to neutralize this. So adding hydroxide ions is essentially the same thing as removing H3O+, right? It's going to neutralize it. For every mole of hydroxide I add, a mole of H3O+ is going to be neutralized looking at this equation. So again, if you would have had this question back in chapter 13, and I said, which way does the equilibrium shift if we removed hydronium ions, which is what we're doing when we're adding hydroxide, you're going to tell me that it shifts towards products, right? I don't have enough of this anymore, so I need to make more of it. It's going to shift in that direction, so we're going to expect this to have a bigger concentration. We're going to expect this to have a smaller concentration. And then again, if I go back up and look at that table, I'm starting out with 0.55 molar. My new concentration is 0.65 molar. It is bigger. My original concentration here, 0.45. My new concentration, 0.35. It's smaller. So just kind of another way to think about it to confirm that you're adding and subtracting correctly, right? It is an application of Le Chatelier's principle when we add the acid or base to it. One more thing that I want to talk about here is buffer capacity. So when I first gave us the definition of a buffer solution, right, we said it resists drastic changes when small amounts of acid or base are added. And I did say it was important that it's a small amount. If you add too much, you actually exceed the buffering capacity of your buffer. And then it no longer buffers, right? We can't neutralize it anymore if we've exceeded a certain amount. So this is a measure of the amount of acid or base that can be added to a buffer or that the buffer can absorb. And we really should say neutralize. We're not really absorbing it, we're neutralizing it, though absorb is commonly used. So that the buffer can neutralize, not neutralizing. So a measure of the amount of acid or base that the buffer can neutralize without a significant pH change. And what this really depends on is the concentration of the weak acid and its conjugate base, or the concentration of the weak base and its conjugate acid, whatever it happens to be. So this depends on the concentration of the weak acid and conjugate base, or weak base and conjugate acid in the buffer. The more concentrated the weak acid and conjugate base, or weak base and conjugate acid, the higher the buffer capacity. So the more concentrated the higher the buffer capacity. So the reason I want to talk about this now is because I think if we go back up and look at our change tables, we can kind of get a handle on how this works. So I'm just going to copy one of those change tables back down just so we don't have to scroll so much. And let's use the first one here. So I'm going to copy this and then I'll go back. So buffer capacity, and I'm going to paste. Oops. Yikes, that got messy. Sorry guys, let me move this out of the way. Let me get this out of the way. Not sure why I'm not getting that. Okay, sorry about that. And then I'm just going to clean this up a little bit. I'm going to rewrite some of that, but I kind of just want to start fresh. So we had our original concentrations, our change, and then our new concentrations. And we said to get our new concentrations, what we do is we take the smaller of the two reactants, right? So I'm looking at these two, right? It's a limiting reactant problem. The one that's smaller is the one that's going to dictate the extent of my reaction, right? I can't react more than I have. So since this one's smaller, I'm going to subtract it from both sides. So we subtracted that from both sides, and then we added it over to this side. If I would have added, so we're going to change up these numbers a little bit. If I would have added, right, 0.3 molar, right? Remember we said small amounts of acid, so I'm increasing the amount of acid. 0.3 molar is still smaller, so I'm still going to subtract that from both sides. Or sorry, from both reactants. I'm still going to add it to the other side. I'm just not going to do that here because I can make my point without it. So this is still 0, right? All of the strong acid that I added is neutralized, right? I've absorbed all of it. I'm going to erase those again. I'm going to increase the concentration again. This time I'm going to increase it to 0.60 molar. Now again, I have to take the smaller of the two, right? This time my smaller number is this. So I'm going to subtract that one from both sides, or sorry, from both reactants, add it to the other side. This time this goes to 0, and I still have 0.05 molar strong acid left. What I've done is I've exceeded my buffering capacity, right? I have some of this that is unneutralized. I have not neutralized it all. And I've used up all of my base component. So at this point, I have exceeded my buffering capacity. Up here, we said that the more concentrated, right, my conjugate acid, sorry, my weak acid and its conjugate base, the higher the buffering capacity, right? The way I could not exceed that by having 0.6 molar is we could make this number bigger, right? If that was 0.9 molar, now I'm going to subtract the 0.6 from both sides. So kind of looking at it, if you're subtracting this number from this number, we're neutralizing all of it. If this is bigger than this, we've exceeded our buffering capacity, right? We've added more acid than the base component of the buffer can handle, which is how I have this example. Now what I have is I have a strong acid, and I would just take the negative log of that number to get my pH, and my pH is going to make a dramatic tumble, right? It's going to go down by quite a bit. So kind of the easiest way to look at buffering capacity, we want the concentration of this to be bigger than this. if the concentration of the acid I'm adding is bigger than the concentration of the base component, I've exceeded that capacity. And we can look at it with the base one also, going back up, right? If I look at the base one, we want the concentration of my base to be less than this. We want this to go to 0. If I have more of this than I do of this, this will not be 0 and I've exceeded the buffering capacity. So there is a limit to the amount of acid or base that you can add to the buffer and still have it neutralize it, right? The more concentrated the buffer solution, the more acid or base I could add to it.